Green's theorem for vector analysis. History. This theorem is named after British mathematical physicist George Green. In 1828, he published a paper titled An Essay on the Application of Mathematical Analysis to the Theories of Electricity and Magnetism, where he extended the previous work of Simon Denny Poisson on the electricity and magnetism. The form of the theorem was first presented by Augustin Louis Cauchy. The first proof of the theorem was given by Bernard Riemann. Introduction. Green's theorem simply gives the relationship between the line integral around a simple closed curve C and the double integral over a region R bounded by the curve. It is sometimes also referred as two-dimensional special case of Stokes' theorem. Principle. Let us consider an anti-clockwise circulation around a simple closed curve C and R be the region enclosed by it. We can consider the circulation to be the result of infinite microscopic circulations inside the curve C. Green's theorem is simply the relationship between the macroscopic circulation and the microscopic circulation inside the curve. Statement. Let R be the region enclosed by a simple closed curve C. M and N be the continuously differentiable functions of x and y. Then, line integral along a closed curve C m dx plus n dy equals to double integral over the region R del x of n minus del y of m dx dy. Proof. Let us take the curve C in such a way that any parallel lines drawn to either of the axes cuts the curve at most 2 points. Let the curve be included between the lines x equals to A, x equals to B, y equals to P, y equals to Q. Let's divide the curve C into two parts, AQB and BPA. Let AQB equals to C1 and BPA equals to C2. Let the equation of curve C1 be y is equals to f1x and for C2 y equals to f2x. Then double integral over the region R del y of m dx dy can be written as, since over the region R x is varying from A to B and y is varying from C1 to C2. Now integrating the dy part, we can see that in the first part the integration is from A to B via C2, which is clockwise. Since we have taken the curve C in anti-clockwise direction, so we have to make the first part in anti-clock as well. So we can simply write the first part as negative of integral from B to A. Since integration of curve from B to A via upper part is simply C1 and from A to B via lower part is simply C1, so we can write, which is again closed integral over curve C. Let it be equation number 1. Similarly, let's divide the curve C into PAQ and QBP. Let the equation of curve C1 be x equals to g1y, and for curve C2 x equals to g2y. Double integral over a region R del x of n dx dy can be written as, since over a region R, when y changes from q to p, x changes from C1 to C2. Now integrating the dx part, we can see in the second part the integral is from q to p via left path, which is clockwise, so we have to make it anti-clockwise. So we simply change the negative of integral from q to p to positive of integral p to q. Since integral of curve from q to p via right path is simply integral over c2, and from p to q via left path is simply integral over c1, so we can write, which is again close integral over curve C and dy. Let it be equation number 2. Adding equation number 1 and 2, we get, and this is the Green's theorem. Application. To calculate the area of conics using line integral. To calculate the amount of work done on a force field. To calculate flux. Example. Suppose a particle travels around the curve represented by x square plus y square equals 9 in a counterclockwise direction. Force acting on the particle is given. The particle starts and ends at point 3, 0. Then find work done. Given x square plus y square equals 9. Comparing with the equation of circle having center at origin, we get r square equals to 9. We know that work done equals to integral over curve C f dot dr, which can be written as, where fx is the component of force along x-axis and fy is the component of force along y-axis. Now substituting the values of fx and fy from the question, we get. Now applying Green's theorem. After solving, where A is the area enclosed by the curve. Since the given curve is a circle, we can write it as, Green's theorem only works if the curve is oriented in anti-clockwise direction.